Hello world, I'm Jonathan Schillinger. This is my happy presentation, my harmonic analysis people's presentations for YouTube. I'm a PhD candidate at Florida State University. I'm going to be graduating soon. And in this talk, I'm going to be discussing a lot of the major results in my thesis. A lot of what I've been doing has been looking at equilibria and asymptotics for the Gaussian kernel. So how this talk is going to work is I'm first going to introduce the problem because the area that I work in is specifically called energy theory. However, as a field of mathematics, it's still fairly new. However, energy theory brings in a lot of ideas of geometric measure theory. It uses a lot of harmonic analysis. It uses some functional analysis. It uses some idea from probability. It also uses a lot of PDE methods, and it brings in a lot of ideas from potential theory. However, the unifying questions that make energy theory its own thing is that it uses a bunch of different results of different areas of analysis to answer one of two questions. And sort of these two questions is what the field has been built up around. The discrete energy problem and the corresponding continuous energy problem. And so the first part of the talk is going to be introducing these two questions and then talking about what I've been doing to make progress in these, specifically in one instance. So my thesis is going to be talking a lot about computing equilibria, and what that means in this context is finding equilibrium measures for the Gaussian kernel in particular. So let's get to it. So what is energy theory? So again, it's sort of energy theory as a mathematical discipline is taking a lot of different areas of mathematics to address one of two questions. The first question is the discrete energy problem. So how does this work? Well, let's imagine you have some set here, omega. Maybe this is some region of space. And let's say you wanted to start placing particles inside of this set. So let's say I have two electrons, say, and I want to place them in omega. So I'm going to put maybe the first electron over here, call this x1, and I'll place the other point here, x2. Let's say I have a third one. Let's say I have a third electron that I place over there. Well, in the electron analogy, after I place the first electron in the set omega, and I go to place the second one, then those two particles are going to interact, right? By forcing them to be there, they are going to repel one another in the electron analogy. So then I know this point is going to affect x2 and x1. And I also know that after I have these 2 points and I place the third one, well, then x2 is going to affect x3, and x1 is going to affect x3 as well. Sort of all of these points are going to affect one another after they're there. But after I place them there, they're going to affect one another. So a priori, I know how x1 affects x2. And so I'm going to assign some number to that, some numerical value. And then this is what I'm going to, the way I do that is going to build up a mapping which maps from the product space into R. And you should think of this K as my way of knowing how does this particle over at this position affect this particle over here. The one restriction I'm going to make is that particles can affect every other particle that I place, but they do not affect themselves. I now need to see, okay, how is this system working? The way I would do that is by summing up all of these interactions. Again, restricting myself to only how the particles affect each other, not how they affect themselves. And then this quantity, I will call the discrete K energy of omega n, where omega n is just the collection of the decisions that I made of the places to place the particles. So in this instance, I would have an omega 3 because I only had 3 electrons, and it consists of those 3 regions of omega, those 3 points that I decided to place the electrons at. Okay, so this is discrete energy, and now the discrete energy problem becomes, okay, how do I make this as small as possible? So in generality, the discrete energy question starts with some metric space and some interaction kernel K, which maps from the product, and it's going to be real valued. We're going to let it take values of infinity just because our configuration needs to be of separate particles, but those particles don't necessarily need to be at separate points in space. So I will allow, say, x1 to be equal to x2. I could try and place 2 particles in the same point, but in the electron analogy, that would sort of have an infinite penalty, right? Because electrons repel each other in general, so trying to place one in the exact same spot where one already is would sort of have an infinite energy cost of doing so. So now I want to make this quantity as small as possible, so I want to minimize this sum over, well, over the choices I made, and the choices that we made in this game were where do I place the electrons. So I'm going to try and minimize this quantity over all possible configurations, and this is what we'll call the minimal discrete endpoint energy of endpoint K energy, depending on what your kernel is. Because in the physical system, we were using sort of an electrostatic interactions, but K can be whatever you want, however you assign an interaction between one point of your set and another. One interesting thing that has come out of the mathematics behind this area, as opposed to all of the physics, which is in the physical scenario, it's sort of obvious that if you start with 2 electrons and then you add a third, the energy of that system can only ever go up. There's no way I can place a third electron without introducing more repulsions. And so the energy of my 3 points will always be larger than, say, the energy of the 2 points beforehand. What's interesting is that mathematically, even if you're not talking about electrons and electrostatic interactions, just inherently from the way this game is set up, that's always the case. There's a traditional result by Fouquet in the 1920s, which is that this sequence of the minimal energy, so not only the energy of your arrangements, but the best possible arrangements, is a non-decreasing sequence. As you add more points, the smallest possible energy can only ever go up. And what's interesting is that it doesn't depend on your interaction kernel. So in the physical system, we're using an electrostatic interaction between K, which is highly repulsive, as we know. But even if you make that interaction attractive instead of repulsive, or however you decide to assign an interaction between points, this can still only ever go up. It doesn't actually matter what K is, which is sort of an interesting mathematical result, which arose from sort of this physical system, this physical way of viewing the scenario. So this is the discrete energy problem. However, I do work more on the continuous side of things. So how do we get from the discrete case to the continuous case? Well, we would ask ourselves the following question. Instead of starting with some region of space and making the decision to place some points, well, what if every point in the set is a candidate for interactions? What do I mean by this? What would be the physical analogy? Let's say you had a sheet of like metal or some electrically conductive material. There's our omega. And then over here, I'm going to attach a wire over there and over there. And then let's say I attach these wires to some battery or power source. Well, then once I hook this, say, a piece of aluminum foil or this metal sheet up to these wires and I flip on the switch, or I connect them to the battery, as soon as I do that, this sheet is going to pick up a charge. But it's not going to pick up a charge at one point. It's going to pick up a charge all throughout. Now, it might not be a uniform charge. This sheet, this piece of metal that I chose might have imperfections in how it was built. Maybe it has some rust. Maybe not everywhere is made of the same metal. And then so you can ask, well, depending on how the size of this sheet, how should it be made? Like what materials should I use to make it and where should I place those materials in order to make this sheet as conductive or as least conductive as possible, depending on your applications. So now in here, instead of choosing points, the choices that I'm making are how do I design the material to pick up charge? Or from the math standpoint, how do I assign an amount of charge on a region of omega? So the choices that I'm making when I pick out this sheet is a choice of measure. So this is where the measure theory comes in. So the way this game works in the continuous setting is you take all of the positive finite sign Borel measures, which are supported on omega. And so you can imagine this as thinking of how your sheet is designed in order to conduct or not conduct the charge after it's hooked up to the wires. Or again, K doesn't need to be an electrostatic. It could be however the object interacts with itself, the set. And then with the setup, we can have two new quantities. The first is the potential of the measure that you chose with respect to that kernel, that interactions, which is what happens when you, instead, before in the discrete case, we were summing up all of the different pointwise interactions. Here we need to do it sort of for all of the infinite points in omega. So the natural extension of the finite sum is the infinite integral. And then we find the energy, the K energy of this set with respect to the measure you chose is going to be the double integral of that kernel or the single integral of the potential. And then we can play the same game, right? How can I design the sheet in order to make this quantity, this continuous K energy, as small as possible? It's sort of like the best possible composition of the sheet. However, before we define what that is, one thing to note is that We usually don't care about the total mass of the plate on the mathematics side. In the materials science, I'm sure the actual amount of material is going to be a consideration, but we generally don't need to know what the total mass or measure of your set is. So it makes sense that we'll normally normalize this. And so we'll usually restrict ourselves not to just finite sign Borel measures, but probability measures, which are supported on omega. But looking for that best possible measure is going to be looking for the measure which makes that energy as small as possible. Since every point in my set is going to pick up a charge after I hook the wires. So I can't choose an arrangement of points, but I can choose how that sheet is designed to pick up a charge. And then this minimal continuous energy has a special name historically because of the mathematicians who are working on this. This is called the Wiener constant or sometimes the Robinson constant, depending on the source. With some mild assumptions, we're guaranteed that there exists some measure mu which will attain this optimal value, and that measure will be called the equilibrium measure for the set or the optimal measure. And sometimes we'll suppress the kernel we're talking about if it's understood. Now, what you might have noticed is that throughout this discussion, when we've introduced energy theory, we've never once used the metric, even though we began saying assume omega is a subset of a metric space when we started throwing the math definitions. The reason we usually want to look at sets which are in metric spaces is because historically there's two significant kernels which are defined using a metric. However, in abstract energy theory, you don't necessarily need a metric. What are those two kernels? We'll talk about them in a little bit. However, how are these two problems related, the discrete and the continuous energy problem? Because for the discrete problem, a lot of the methods which are used are sort of linear programming, probability, a lot of coding techniques. However, on the continuous side, it's a lot of geometric measure theory, it's a lot of harmonic analysis, it's a lot of calculus of variations. How are these two questions, how is the interplay between these two problems? They're actually just two ways of viewing the same thing. And this is a historically relevant result by Chiquet, also in the 1900s, which the sequence we looked at before that Chiquet showed was non-decreasing, the energy is only ever going up in the discrete case. This limit of that sequence is also called the transfinite diameter of your set with respect to that kernel. What Chiquet showed in the 1950s is that this limit, when it exists, is the same as the continuous energy. So in 1958, in a technical report, Chiquet showed that this transfinite diameter is equal to the continuous energy. And not only that, but when you're trying to look for measures, there's nothing saying that those measures can't be discrete, which is almost the same thing as picking out points in a discrete setting. And if you look at any of those normalized point mass distribution measures, those will converge weak star to the optimal measure in the continuous setting. So these two questions really are asking the same thing. Looking at the discrete problem and looking at arrangements of points. In the limit then, will tell you the information about the optimal measure in the continuous setting. Likewise, the continuous measure will give you some geometrical information about where you might want to place optimal points in the discrete setting. Now, let's get back to that metric question. So historically, those two kernels that use a metric to define themselves are the Riesz kernel and then also the Gaussian one, which we'll talk about in a bit. The Riesz kernel is just the reciprocal powers, or the family of Riesz kernels, are the reciprocal powers of the distance. Okay, so this is almost like the electrostatic one, right? Because the electrostatic interaction between 2 points is proportional to the inverse of the distance between them. So that's like the Riesz kernel with S equal to 1. Now, when we were talking about Riesz energy, and later when we talk about Gaussian energy, both of them depend on a parameter. Riesz depends on S. We'll see that the Gaussian one depends on an A value. We'll generally suppress the K in the notation and just give you the parameter if it's assumed we know which kernel we're looking at. Now, the special cases of the Riesz kernel, which are historically significant, are what we've been using in this entire analogy, the electrostatic or the electron analogy. Well, that is exactly the Riesz kernel in R3 when S is equal to 1. However, in general, these kernels are called the Newtonian kernel or the harmonic kernel if you work in Euclidean space with your Riesz S parameter equal to D minus 2. Why are they called that? Well, the reason they're called harmonic is look what happens in the plane, so in R2. So if we're looking in R2, the Riesz kernel, which would correspond to the harmonic one in R2, looks like it should be the S equals 0 case. but S equals 0 is just a constant kernel. However, instead of looking at S equals 0, what people generally do is they use some limiting process. So the behavior of this kernel as S gets small, if you want to investigate that, you'd probably want to look in the limit of your kernel in the difference quotient as you get smaller. And this is exactly the logarithm of the reciprocal distance. Why do I bring this up when I talked about the plane? Well, in R2, the fundamental solution to the Laplacian, which is the defining equation of a function being harmonic, is the log, right? So log of 1 over r in the plane is the fundamental solution to Laplace's equation. And so this is like the kernel of the Riesz energy in the harmonic setting. So if you're looking in RD and you're looking at S equals D minus 2, in general, those are called the harmonic cases. Now, this is all Riesz kernel related stuff because historically this field was developed out of the electrostatic interactions and sort of the theories of the atom and particle and subatomic particles, which were being developed in the 1900s. However, notice that the Riesz kernel has a problem, right? We were allowing ourselves to try and place points in the same spot. But for harmonic values or harmonic values of their parameter, when you have the reciprocal distance, that function has a singularity along the diagonal and it blows up if you try and place points at the same region. So these kernels aren't exactly the nicest things in the world to work with. So instead, let's look at a nicer kernel. So within a different parameter, we'll call this A, which we restrict ourselves to only be positive. It can't be negative and it can't be 0. Then the Gaussian kernel is defined as the exponential of your metric squared with minus this parameter. Now notice these kernels are great. Not only are they lower semi-continuous like the other Riesz kernel was, and what we usually want our kernels to be in energy theory, they're continuous in the actual sense. This is sort of like the nicest function you can think of in an analysis setting. It's not only continuous, it's smooth, it's great. It has no issues, no singularities, no regions where this kernel blows up. And while a lot of work is known, the Riesz kernels have been studied to death throughout the 1900s because of their applications to physical scenarios. The Gaussians were generally left alone. That's not to say we didn't know anything about them. We know a lot about Gaussian kernels and sort of how their energy works to some extent, but people generally didn't care as much because these weren't the settings where there was that strong connection with PDE's, Laplace's equation, and physics with the electrostatic interactions. To some extent, this is starting to be picked up now. And so what me and Dr. Reznikov did is, okay, well, what can we know about the Gaussian kernel? People didn't know what the measures were for these things, what the optimal configurations were. Let's see if we can find them. And the reason we did this is because originally this was a question that one of Dr. Alexander Reznikov's students had worked on before with the Riesz kernel. We were able to get a result for that using Gaussian results. So how we're going to do that, let's introduce some little bit of potential theory because this is going to be how we computed these things. I'm not going to give proofs. This is sort of like a preview for the paper, which is going to be coming up soon by the end of this year. I'm just going to be giving sort of a sketch of what we did. So in order to do that, you need to know a little bit of potential theory, really just this one result from Bjork in 1956, which is the minimal measure. If you look at the potential function of the minimal measure is going to be constant on the support of that measure. And that constant is your energy because we're looking over probability measures. And as soon as you leave the support, this potential function can only ever go up. It can only ever increase. And this is a necessary condition for a measure being optimal. So a great way to try and find optimal measures is to start throwing measures into your energy functional and start to see if you can show that where these energy functionals have minima. Because then those minima will be the support of your measure, restrict it there, and then it's a good candidate for what the optimal measure might be. So now let's start computing them for the Gaussian kernel. Let's start with an easy set. So let's start with the interval, and let's assume we have some optimal measure. So mu a is going to be the optimal measure for the Gaussian kernel of parameter a. Now, what happens if we integrate this once? So what does our potential look like? Well, it looks exactly like this, which isn't interesting. Now I know on the support, this thing needs to be constant. How do I leverage that to tell me what this measure might be? Well, here's what I'm going to do. Let's extend this function. So originally this potential is defined for the interval -1, 1, and it's not really defined outside of it. However, because the Gaussian kernel is so nice, the definition naturally can get extended. So I'm going to view this as not a function from R, but I'm going to view this as a subset of the complex plane. and I'm going to take some open set V around our interval. And then I'm going to extend it and look at the function defined there. Okay, so now my function is a function of Z rather than of a real variable. Now, I know the Gaussian kernel has a finite energy because the Gaussian kernel is so nice on this set, right? I know there exists some optimal measure, and I know the energy is going to be finite because the set is compact and my kernel is continuous in addition to being lower semi-continuous. So I'm going to define an auxiliary function where I subtract this potential from that energy value. Even though I don't know what it is, I can still make this function. Now, this function is analytic on some open region of the plane. So now if I want to look at where this function is zero, there's a lot of analytic function theory about zeros of analytic functions. I know that the zeros of an analytic function are isolated or my function's constant. Well, is my function constant? No. It's easy to see if you differentiate our auxiliary function here. So you're going to have our negative 2a z minus y d negative a z minus y squared, and then inside the integral. And trivially, this is not a constant, unless it's constantly zero. However, if it was constantly zero, this would imply that the measure that we threw in was the zero measure, which isn't a probability measure. So I know this function isn't constant, so I know its zeros need to be isolated. However, those zeros are exactly where my potential function would be equal to the energy. So those zeros would be the support of the measure. And that means that the support of the measure is discrete. So the optimal measure for the Gaussian kernel over the interval is going to be some discrete collection. And so in generality, what we're able to show is that for the interval, if you take some interval and you look at the Gaussian kernel, you're always going to have some collection of point mass measures, and it's a probability measure one. So you have these weights, beta, which depend on I and A. Now, for small values of A, what do these look like? Well, originally, for small values of A, our support originally is going to be supported at the endpoints of the interval. However, there is going to be an area of A values, a critical A value, where you necessarily need to increase the cardinality of support, and then it'll jump to 3, and then it'll only increase from there. And we're also able to show that this measure will converge weak star to the uniform measure, uniform probability measure over the interval. Okay, so this is lambda is the Lebesgue measurement. Well, what do these potentials look like? Well, they look like the following. So originally, before you hit that critical A value, our measure is supported on either endpoint of the interval, and that's also the global minimum of the potential function. The theorem from Bjork says you're constant on support, so I'm constant at these. I have the same value at either endpoint of the interval, and then after I leave that, the potential needs to only ever go up. However, because our optimal measures are point masses, our potential function is just a sum of Gaussians with those coefficients in front. So you can imagine that this curve is built off by some really wide Gaussian distribution centered there and one really wide Gaussian distribution centered here. And then so as you move to the left, you pick up more of the other curve than you're losing in this distribution. But as A gets larger, these distributions become thinner, and eventually I'm going to have something like this, where the overlap between the two is small enough that the middle of my potential is going to dip. And eventually it'll dip far enough that I'll hit that critical mass, that critical parameter where I equal to the same value I am on the outsides. And because I need to be constant to the energy on the support, this will tell me that at some point I'll need to include an extra point in the support. So eventually I start off only being supported on either endpoint. And then as A gets larger, I need to include the middle. And then after that, again, the same thing happens when the Gaussians get too thin, where the overlap decreases enough. So then I'll have a sag in the potential. And that's going to happen again between two of those distributions. So I'll need to add 2 more points and so on and so forth. Okay. So as A gets larger, the support increases, and eventually you end up being supported on the entire interval in the limit, because eventually you approach the uniform measure. Great. So this is some nice stuff about the Gaussian kernel over the discrete problem for the Gaussian kernel. why is it a discrete problem? Because this is all continuous stuff. We started with a potential theoretic result, which works for the continuous side. Well, all of these measures are discrete, so these also then necessarily have to be optimal arrangements for the discrete problem. Great. So let's look at a different set. The interval is great because it's in simplicity. Let's get a little bit more interesting. Let's look over the disk. So what we're going to leverage over the disk is another potential theoretic result, which not only the one from Bjork, which says that it's constant on the support and you can only ever increase by leaving the support, but there's also a well-known result in the 1970s in Landkoff's book on Foundations of Modern Potential Theory, which says with some conditions which are met by the Gaussian kernel and the closed disk, not only do you have an equilibrium measure, but it's unique. So then if I can find a measure which is constant there, I'm guaranteed not only that it's an optimal measure, but it's the unique one. And why does this help me over the disk? Well, over the disk, a natural choice to use is, well, what about the boundary, the arc length measure along the boundary, right? Sort of that's the natural measure a lot of people use because of potential theoretic reasons. And it just so happens, if you throw in the surface measure, meaning the one supported on the edge, into the disk, it's rotationally invariant and the potential is constant there. So then for small values of A, that measure is the minimizing measure for the Gaussian kernel over the disk. So for small values of A, your measure is just going to be on the edge. But what happens as A increases? What's interesting is that, okay, let's look at what we have here. So we have our disk. And originally our measure is only supported on the outer edge. But what happens if you take a slice through your disk, say the x-axis, and restrict yourself to looking just there? Well, then you have a measure which is supported here and here as a subset of the interval. And what we know for the interval happens is eventually, yes, you're supported on the edges, but as A gets larger, the interval said we eventually need to include the center. So then there might be a range of A values where the optimal measure for the disk is supported at the center, at the singleton point in the middle, plus the boundary. And lo and behold, after some computations, that's exactly what happens. If you plot radially the potential of the Gaussian kernel over the disk for larger values of A, because for the first few ones, you will only be supported at the edge, at the disk, eventually you'll reach a point where you will need to include the center and the endpoint. And then as A increases, just again like the interval, you're again going to have some critical A value where you will need to include another point here. However, this is a radial plot. So what this implies for the Gaussian kernel over the disk is that as A increases, you will be supported on a family of concentric circles. And then eventually these circles, how many there are, will increase as A grows, and eventually it'll fill out the disk. And eventually the minimal measure over the disk will eventually converge to, again, the normalized uniform measure over the disk. So Lebesgue measure over pi r squared. Now you're working over the unit disk, but this is the same thing no matter what radius disk you're looking at. So we also computed the equilibrium measure for some other sets, but this is just a preview, and so this is sort of a little plug. You'll have to read the paper, not only for the full arguments and computations about all of the justifications. Again, I'm not giving any proofs here. I'm just sort of sketching out the ideas. But we also looked at the ellipse and some fractal sets as well. Now let's go into the asymptotic part of this talk. So before we end, so sort of the other stuff we're doing is we're not only computing equilibria, but then how does our energy behave as the parameter grows? Well, if you have a compact set of ambient dimension, a subset of Rn, and your set also has dimension n, so Hausdorff dimension n, well then the asymptotics of the continuous Gaussian energy are of the order a to the negative dimension over 2. Okay? That's the same thing as saying that this limit exists. The way this is proven is through a simple Fourier argument, and this only gives us that we can show that a limit is increasing necessarily in A, so I know the limit exists as an extended real number. You need a little bit more than just having the same ambient dimension. You also need a little bit of a smoothness condition on the boundary in order for this limit to be finite as well. What's interesting about these asymptotics, though, is, okay, this is maybe what you would have guessed. However, what happens for fractal sets is also what you'd expect, which fractals are a little weird, so it's sort of surprising that this happens. So if you look at specifically a self-similar fractal, So by self-similar, I mean that it is the unique fixed set under some family of similitudes. So if I give you some rotation and shifts, then there is some unique compact set which is fixed under all of these, sort of the different leaves of the fractal. So for example, the usual Cantor set is generated by two similitudes, the first one being x over 3 and the third being x over 3 plus 2/3. And so the first one gives you the left half, the left leaf, and all of the points that are there, and the second gives you the right half, the right leaf, and all the sets which are there. Well, the asymptotics for these sets where they have dimension less than 1, because they're a subset of R, but they're not of dimension 1, they're strictly fractal dimension, the order of the asymptotics are the same as the order for the nicer sets, the ones which are not only a full dimension but smooth, which is an interesting result. Interesting because fractal sets don't normally behave. And again, we're looking at specifically a subset of self-similar fractals. So even though I gave the example of the Cantor set has the one contraction ratio. So R1 equals R2 and it equals 1/3. And so those are not algebraically dependent. Algebraically dependent is just a condition saying that if you look at the span of those ratios as a subset of R, whether that span is dense or not. However, this isn't dense because the span of 1/3 is just a copy of Z multiplied by 1/3. What's powerful about this result is this is related to a Riesz result. So a Riesz result in fractals, which came out by Califf in 2010, is that you get a similar result as this, that as the S parameter in the Riesz energy approaches the ambient dimension, then you get sort of a similar power of asymptotics, is what we're saying here for the Gaussian case. However, that argument relies on some second order density results, which are specific to the Riesz kernel setting. However, this result here, we're able to show in the paper, actually implies the Riesz result, because the Gaussian kernel is related to the Riesz one through a gamma function definition. But not only that, this not only implies the Riesz result that Califf found in 2010, Califf's result was specifically for the Hausdorff, relied on some knowledge of the Hausdorff measure on fractal sets. This shows that even though the Hausdorff measure isn't the optimal one for the Gaussian kernel, although the optimal ones will approach it in the limit, any measure for which this limit is finite, so not the optimal measure here, but so we wouldn't be looking at the energy, but if you look at the limit of the energy, the Gaussian energy for some other measure, mu, if you know that in advance this limit exists, well, then this implies that the limit in the Riesz setting of that same measure also exists and is finite. And we have an explicit relationship between how these two values are related, right? We computed it explicitly. Okay, so that's a sort of plug for the paper coming out soon. This is an overview of some of the stuff that I've been working on and which will be in my dissertation in the spring. Thank you so much for taking time out of your day to listen to me talk about what I've been doing for the past few years. I'd like to thank my advisor, Dr. Alexander Reznikov, as well as Dr. Doug Hardin, Dr. John Hoffman, and Dr. Austin Anderson. Dr. Doug Hardin is at Vanderbilt, and he's one of the founding fathers, and I've had discussion. I got to meet him, and we've had discussions about some of this. And Dr. John Hoffman is a postdoc who has been working with me on some of, me and my advisor on some of the analytic function results that we got for the Gaussian measure of the interval. And Dr. Austin Anderson is one of Dr. Reznikov's previous students who knows more about fractals than I and helped for some of the discussion. So thank you so much. I started this talk by saying hello, world, and goodbye, world.